Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class, and I'm putting it online in case it would be helpful to others as well. In this first section of Chapter 4, well, it's more of a group of sections that I put together. We are going to talk about what is known as curve sketching. Before I forget, I should say that there is a link to a printable set of guided notes in the description of this video that you can use to follow along with what I go over in this lesson. All right, so back in Chapter 3, we spent some time talking about how a function's graph related to the graph of the derivative. And we're going to sort of continue that discussion here as one of our first applications of derivatives. However, we're going to take it a whole lot further than just matching functions with their derivatives graphs. So what I want to do in this warm-up is I want to start by talking about some basic things that you need to be able to identify on a curve of a function, or you need to be able to eventually sketch for yourself. Okay, let's start with something that may seem obvious to some people, but I always feel like I have to mention it. You read a graph the way you read a sentence, meaning from left to right. So when I ask you where is the function increasing, that means from left to right, when is it going up? I've had students argue, look, from G to F, I'm going up. That's reading the graph in the wrong direction. Okay, so keep that in mind, left to right. The directions of this warm-up say to use the letters marked on the curve above. Using the letters marked on the curve above, identify intervals of points for each part. And so this little warm-up exercise is just to get you used to all of the different words that you're going to encounter when talking about the graph of a function in this lesson. Okay, so what I usually ask my students to do when I am teaching this in class is I ask them to do as many as they can on their own. And they probably don't know what to write over here in this notes section. I'll definitely make sure to go over that in detail. But I suggest you do the same for this video lesson, meaning you pause the video right now. You try to do as many of these as you can on your own. If you're one of my students, I probably already recommended that you do that before you watch this video. And then what I'm going to do is I'm going to pause the video and put the answers, and then I'll go over each one with some notes. Okay, I'm back. Here are the answers to the warm-up. And I first like to mention that some of them, notice, are intervals along the x-axis, while others are just x points. Okay. What I want to do now is go through each answer and write some notes. And the notes that we are going to write are always going to be notes about either the first or the second derivative of the function. Let me show you what I mean. Okay, so for increasing, I got the interval from A to B and the interval from D to E. Okay, so again, we can see if we go from left to right that the graph is going up on the interval from A to B, and it is also going up on the interval from D to F. Totally knew that that should have been F. Okay, I had it on my paper as F too. All right, we fixed it, we're good. Okay, anyway, I'm not editing that out. It's not worth it. You get it, right? I made a mistake. Okay, anyway, what can we say about the derivative? Anything about the derivative when the function is increasing? Do you remember? Well, remember, derivative is slope. So if you think about a line that's going up, that's increasing, what do you know about its slope? It is positive, right? Same thing happens for a curve and the derivative. Anytime that your curve is increasing, your derivative is positive. So the note that I would like to write right here for number 1 is that f prime is positive. Okay, for the next one, we have that the function is decreasing from B to D and from F to G. By the way, I don't know if you noticed from my interval notation here that I only use brackets around endpoints when I am talking about increasing or decreasing intervals, and the same thing with concavity you'll see later on. If it is an interior point, I like to use a parenthesis because it's a point of change. Different places use different things for that rule, okay, but that's what I like to do. I like to, again, use brackets for endpoints and parentheses for interior points when I am addressing intervals of increasing, decreasing, concave up, and concave down. All right, so first I'll highlight on here, we are decreasing from B to D and from F to G. I don't think I made any mistakes with that one. Nope. Okay, and what we will write for that one is the opposite of what we wrote for 1, right? Whenever the function is decreasing, the derivative is negative. That's a G. All right, next. Horizontal tangents. I found horizontal tangents at x equals b, d, and f. Okay, at x equals b, d, and f. The tangent lines that we would draw would all be horizontal. We already talked about that at some point in chapter 3, right? What we said there was that whenever we have those smooth turning points, that's where our tangent lines will be horizontal. And what do we know about the derivative values for horizontal tangents or smooth turning points? I hope you remember that that's where the derivative is equal to 0. That is going to be a pretty important thing to know as we work through this section. Okay, next, how about absolute maximum and absolute minimum? Okay, so I found an absolute maximum at x equals f and x equals g. Oh, I think I decided I wanted to use blue for maxes and red for mins. I don't know. Just go with it, okay? I have weird ways of deciding my color choices. Okay, so at x equals f, I have an absolute maximum. Let me note that. At x equals f, I have an absolute max. And the wording absolute, I'm not sure if you're familiar with that or not, but the wording absolute means it is the highest point of them all. Right, on this interval from A to G, where's the highest point of them all? Because we do have some other high points, but this is the highest of them all, and that's why we're calling that the absolute max. I think I will just note for right now that x equals b, just because I already have this color chosen, x equals b is a relative max. It's not the highest of them all, but it is a peak in that interval. Okay, so we'll call it a relative max. And then let me grab red and I will identify the absolute min. Where's the absolute min? I said it was at x equals g. Right there. It is the lowest point of them all, so that's why we call it the absolute min. Okay, however, notice that I also said that at x equals a and d, we also have mins, minimum points, lower points, right? But they are not the lowest of them all, so we call them relative mins. Okay, so maxes and mins, whether they be absolute or relative, we call those extrema. And what I want to talk about now in the little notes section here is how to recognize extrema from your first derivative. Okay, there is a way to recognize extrema from a second derivative, but we're not quite there yet, so let's hold off on that idea. Let's just talk about how to recognize a maximum from a first derivative. Okay, first of all, I'd like to mention that x equals f, it was a horizontal tangent point, right? It's kind of important to actually note what kind of point you have here. X equals f was a horizontal tangent point, or I'm going to say that was where f prime was equal to 0. Okay, and then what happened was that the graph was increasing to that point and then decreasing. Okay, or a way that we can note that as what is going on in terms of our first derivative is that f prime changes from positive to negative. I'm just going to put plus to minus because I'm kind of running out of room there. So again, it was f prime was equal to 0 and f prime changed from positive to negative. Okay, what about that absolute minimum point? What can we say about it? Okay, x equals g. First of all, it's not a horizontal tangent, right? It's not one of these three where f prime was equal to 0. So is there anything special about it? I'd say there is. It's an endpoint, right? I think that's important to note here. X equals g is an endpoint. And actually, that's all I noted about it for right now. I think we're going to need to see a little bit more information before we know anything in particular about endpoints and how to identify them as maxes or mins. Okay, I mean, I could say that f prime, it is a right endpoint and f prime is decreasing to the left of it, but I think that just sort of confuses things. So I'm just going to stick with it's an endpoint for right now. Okay. All right, next, let's move on to the relative max, which was x equals b. I want you to notice something again about this one. It is, again, one of our horizontal tangents, right? And it was, again, a place where the graph was increasing to that point and then decreasing. Or you could say that the derivative was changing sign from positive to negative again. So that's kind of something that you can say is an important thing to look for maximums, is that you have a place where the derivative changes from positive to negative whenever you're looking at one of those turning points. Okay, that is important. Next, let's look at the relative mins. We have x equals a and x equals d. Okay, well, x equals a, again, was an endpoint, right? And once again, I'm just going to sort of leave it at that for right now. X equals a is an endpoint. And so look at that. We have another endpoint that ended up being an extreme value, one of the extrema. You know, there's more we could say about it, but I think for right now, that's just key to note that both of our endpoints ended up as maxes or mins. Okay. However, there's a lot of stuff we could say about D. Okay, and it's going to be similar to what we said about x equals b and x equals f. Notice D is our other horizontal tangent. So it is, again, a place where f prime equals 0. Okay, it was another turning point. But it is decreasing to that point. The function's graph is decreasing to that point, and then it is increasing. Or what can we say about the derivative? The derivative is negative on the left of that point, and then it changes to positive. Okay, so we can say f prime equals 0 at that point, and it's a point where f prime has changed around it from negative to positive this time. Just squeezed it in. Okay, these are all really important things to know as we move on later in this set of notes, to talk about finding extrema, extreme values of our functions. All right, next, we're going to switch gears a little bit here toward the end of this warm-up, and we're going to talk about concavity. Now, sometimes I find that this is the first time students are learning about concavity and how to read concavity on a graph. Not always, but sometimes. So I'm going to try to go over concavity in a little bit more detail than when the function is increasing or decreasing, because we're used to that. Okay, concavity is the curvature of the graph. It's how the graph is being curved. So, I'm just going to throw something out here right now. Let's just add a page for a minute. If I tell you to draw a curve that is increasing, then decreasing, okay, a curve that's increasing and decreasing, you're not necessarily going to have to draw something like this. This is typical increasing then decreasing, right? Going up, then going down. But really, you could draw something like this, increasing, then decreasing, right? And you've met the requirements of what I asked you to do. So what's the difference between this graph and this graph? Well, it's the way that you curved the curve, right? Or that is known as the concavity. Now, we can say all sorts of things about the derivatives of your function when it's concave down. This, by the way, is concave down, or versus when it's concave up, like this. Okay, but for right now, I just want you to sort of be able to recognize concavity, and maybe we'll talk a little bit about its derivatives and what's going on there. Okay, so first of all, let's talk about why is from C to E concave up. Okay, let's look at C to E, that is concave up. Something really simple that I tell my students to start with if they're just starting out with understanding concavity is that they're looking for a U or any sort of portion of a U for concave up, U for up, okay? So, this is not a U. It's an upside down U. We don't like that. Okay, this from C to E is a U. So we call that concave up. Sometimes you don't see the full U. Here we kind of do. Okay, so that's why we have concave up there. Concave down graphs, okay, here's what I say for this, and I know this is kind of elementary, but this is what I say. I say concave down is like a frown. Concave down is like a frown. Like this, from A to C, that is concave down, and from E to G, that is concave down. Okay, I'm not going to get into too many other colors here, though. What I'm going to do is I'm going to note this. Point C and point E are the places where our concavity changes, right? That's where our concavity changes. And what we call points where the concavity changes is points of inflection. And if you can identify points of inflection, you can then probably pretty easily pick up on where is your graph concave up versus where is your graph concave down, because those points clearly mark the change in the curvature. Okay. So again, what you're going to see here is concave up is where you have the U or any part of the U. Concave down is where you have a frown, and wherever it changes, we call those points of inflection. Now, what can we write over here for our notes? Okay, this is going to get into a little bit about the derivatives, and we're going to talk a whole lot about this as we keep going, okay, because this is pretty complicated to understand at first. But if you look at a concave up section, so I'm looking at from C to E, and at any point in a concave up section, you draw a tangent line. First of all, that tangent line is going to be underneath the graph. Look at this one, it's underneath. Underneath. Okay, so concave up sections, your tangent line will be under the curve. But another thing that's important to note is that the values of the slopes of the tangent lines, or in other words, the derivative values, are actually increasing as you move left to right in a concave up section, or an interval, I should say. Okay, that's kind of hard to see, but try to stay with me here. These first few tangent lines that I drew, maybe the first couple, I guess, here, are negative, right? Negative, negative. They then switch to 0, which is increasing, right? If you go from a negative value to a 0 to 0, you are increasing. And then further on, they go to positive. So negative to 0 to positive means that these tangent line slopes are increasing, and that means your derivative is increasing. So I'm going to say that whenever you are in an interval that is concave up, f prime is increasing. Okay, f prime, not positive. Notice I didn't say positive. I said increasing. There's a difference, right? Some of those f primes were negative. One was 0. Some were positive, but they were increasing from left to right. Okay. Now you actually can say from there that something is positive. If f prime is increasing, that means the slope of f prime is positive. Oh, what did I just say? I don't know if that makes any sense to you, but I'm going to try to talk to you about it again at other points so it does make sense. Okay, f prime is increasing. The slope of f prime is positive, and that is actually saying f double prime is positive. Does that make sense? I'm on a video, so you can't tell me if that makes sense. I know, but you better tell me. If you're one of my students, you better tell me in class or on Google Classroom if that makes sense or not. Okay? And then we're going to say the opposite for concave down, but before we write it, I should probably show it to you here in one of these concave down sections. Okay, from A to C is concave down, and first of all, if I were to draw tangent lines along a concave down interval, they are all above the curve now. See that? They're all above the curve. That's characteristic of a concave down interval. Okay, secondly, as you move from left to right through a concave down interval, they are decreasing in value. The slopes, I should say, are decreasing in value. So you're starting with sort of a steeper slope here and then not so steep, but both of these are increasing, so they are positive. It moves to a 0 slope, and then it moves to a negative slope. And that happens again here. If you would want to draw some tangent lines, you can. Okay, but what I'm going to say for sure is that for concave down, f prime is decreasing, which means f double prime is negative. Okay, finally, what can you say about a point of inflection? Well, if your points of inflection are where the concavity changes, that's where the sign of the second derivative is changing, either from positive to negative or negative to positive. And so that definitely means, because of the sign change, that f double prime is going to be equal to 0 at those points. All right, so our notes over here, just so you know, they have a lot of really important information. However, it's not a full picture of everything that you need to know to be able to understand the relationship between a function, its derivative, and its second derivative in order to do curve sketching or to, solve problems in this application section. But it's a really good start. So if there's anything that you don't understand here, please reach out to me, because as we keep going, we sort of talk a little bit more formally about this stuff. Okay, and if it doesn't make sense here, as we start to talk about it in definitions and theorems and things called corollaries, it's all going to become a jumbled mess. That's a really great way to end this little section and move on. I'm sorry, it's not going to be a jumbled mess. We are going to be okay, right? Look at this. We have a rainbow of definitions here. All right, so let me tell you, my plan for the rest of this video is to sort of just click through these definitions, and then there will be theorems, and then there will be corollaries, and finally there will be tests. And I might talk here or there about a little bit of it, but you might want to pause the video at different points to take this information down if you're writing it down for yourself. Because I don't think I'm going to spend enough time on every single slide for you to write everything down before I move on. Okay, I am going to hit some really important points, though, on each slide so that we sort of understand what we're doing here as we start to talk about this information more formally. Okay, for example, one of the most important definitions to know by heart on this first slide is critical point. Okay, that's probably a new word for you. A critical point is a point in the domain of a function at which f prime equals 0 or f prime does not exist. Okay, the reason critical points are so critical, I mean, look, they're called critical points. That must mean they're important, right? The reason they're so critical or important is because they are going to be your possible extrema. But I also want you to know that other possible extrema are endpoints. Okay, critical points are different from endpoints. And we will focus on critical points a whole lot as we work through some examples in this section. But I don't want us to forget about endpoints as well. Those are just sort of special points that can also be extrema. So let's put with endpoints. And as we practice together in class, you'll hear me say it a lot. Extrema come from critical points and endpoints. Okay. So whenever you're looking for absolute extrema, that's when you definitely need to make sure to consider critical points and endpoints. I'll show you why when we talk about a particular theorem. Usually when you're just looking for relative extrema, that means you're not on a closed interval, so you don't have endpoints, and that's where your critical points are so key. And so, these definitions are here to refer to, but again, I don't think I'm going to read all of that stuff. I'm going to move on to the next slide. If you need to pause it to write that information down, you can. These are formal definitions that you may want to refer to at some time. But again, I'm not going to take too much time in this video to discuss them. Okay, let's move on to a couple of other definitions though, and these ones are pretty important to discuss. A point of inflection, we already talked about this in the warm-up, but it's really important, so let's say it again. A point of inflection is a point where the graph of a function f has a tangent line. That basically means that it's not a place where the function is undefined or the first derivative is undefined, okay? And where the concavity changes. So, whenever you have that changing from a U for up into a frown for down, or vice versa, that's where you're finding a point of inflection. Okay, the most important thing to note in this definition, I would say though, is that at a point of inflection, f double prime equals 0 or does not exist. Okay, I'll talk about that when we get to some examples. And changes sign. In some point in this video, we will talk about something called the concavity test, and that is where this information is going to become pretty important. Okay, along with this information, here's what you need to know about how to spot where a function is concave up versus where it's concave down when you are analyzing its second derivative, which is, as you're going to see soon, it's going to be something you're going to want to do whenever you're curve sketching. Okay, analyzing the second derivative is the easiest way to figure out concavity. So a function is concave up if f prime is increasing, but more importantly, I think we should focus on this. It is where f double prime is greater than 0 or f double prime is positive, right? Greater than 0 values are positive. It is concave down where f prime is decreasing, or that's where f double prime is negative. Less than 0 means negative. 0 is not included because remember, if it is equal to 0, then that is a possible point of inflection. Okay, so now that we're through the warm-up and the definitions part of this set of notes, I think it would be important before we move on to talk about what is one of our goals for today. Okay, well, one of our goals is to get to examples, and we're not going to do all of the examples in this video, but we're going to do a few, okay? One of our goals is to get to the example section in this set of notes where we put all the information that we're talking about here together to do something like this. Take a look at the directions. Use analytic methods to determine extrema, intervals of increasing and decreasing, points of inflection, concavity, and other relevant information such as discontinuities, asymptotes, etc., to sketch the curve of the given function. Okay, so we're going to try to sketch the curve of this cubic function today in this video. Okay, I'm showing you that because we still have a ways to go before we get there. And what's standing in our way are theorems, corollaries, some other information, and discussing all of the different testing you could do with derivatives. Okay. Now, like I said before, I'm not going to spend time on every slide, enough time on every slide for you to probably copy everything down. So I'll let you decide if you want to pause the video at some point to copy before you hear me say anything about it or how you want to do that. But again, what I'm going to do right now is sort of quickly go through these slides where we have theorems, corollaries, and such to point out some important information to then be able to get to that first example. Okay, the first part of your theorems, we have what are called the value theorems. We actually have them all here, which is pretty exciting. All of the value theorems that you learn in this class are here on this page. The first one, the intermediate value theorem, we actually don't reference explicitly in this section, but I put it here just to remind you that that was the first value theorem that we learned. Again, I don't really have much to say about it right now. We sort of just intuitively use it whenever we do curve sketching. Okay, the extreme value theorem, though, is a new one, and this one will be important for examples where you are asked to find absolute maxes or mins. All right, so the extreme value theorem says that if you have a continuous function, but also you are looking at a specific closed interval of that function, meaning there are endpoints. Okay, those are the conditions of EVT, or the extreme value theorem. Then the theorem says that f has both an absolute maximum and an absolute minimum on that interval. So what you need to know about that is basically if you have these conditions, a continuous function on a closed interval, remember it has to have endpoints, then you will be asked to find absolute extrema, okay, meaning we will specifically be looking at that wording, absolute extrema. However, if you are not looking at a continuous function on a specific interval with endpoints, you can drop the word absolute when you talk about maxes and mins. Next, we have the mean value theorem, which is a pretty important theorem in calculus. However, in this first section, we just use it a little bit. We more specifically use Rolle's theorem, which I used to not even teach, to be honest with you, because it is just a particular case of the mean value theorem. And we use Rolle's theorem more often in this section because we usually are looking at places where our function at some point is equal to 0. Okay, but again, they're here for us and we're going to touch on them in this section just a bit, but we will come back to the mean value theorem a couple of different times throughout this year. Okay. So again, you might want to pause the video and write this information down. I will go back and reference it when it is needed. Next, on the next page of your notes, you have some corollaries and other important information. Okay, these are statements, I should say, that follow from the theorems. So after these theorems are proved, these corollaries or other important information are things that you can say for sure because we have these theorems set into place. One of the important ones is that if you are looking for local maxes or mins, then that's going to be at your critical points. Remember, this is the definition of a critical point. So again, an important thing to note here is that if you are looking for maxes and mins and you don't have endpoints, then where are you going to find them? You're going to find them at those critical points. Okay, this is information that we pretty much already know. If f prime is greater than 0, or in other words positive, then your function is increasing. If f prime is less than 0, then your function is decreasing. Okay, and finally, the other 3 corollaries or important information are kind of exciting. We're not going to reference them very much in the curve sketching examples, but we will see some other examples where we will use them. If f prime equals 0 at each point in an interval, then your function is constant there. Does that make sense? If the derivative is 0 everywhere, then that means you're dealing with a constant function. Okay, that statement actually opens us up, though, to some more exciting statements, such as this one. If the derivatives of 2 functions match, then those derivatives differ by just a constant, meaning they don't have to be the same exact function. They could differ by a constant. Think about it like this. If I have, f of x equal to x squared and g of x equal to x squared plus 3, okay, think about that. Both of their derivatives would be 2x. Would you agree? Both the derivative of x squared and the derivative of x squared plus 3 is 2x. So the derivatives match, but the 2 functions are different because of the constant. Okay, and the derivative of the constant goes to 0, and that's why this is the case. Okay, but then this gets into, I put this one in pink because it's so exciting and fun. This gets into discussion of antiderivatives, meaning if you're looking at a derivative and you don't know the original function, can you find it? Yes, you can. Some of you asked that actually as your stupid question whenever we had our last stupid question session. And I was so excited to see that question because the answer is yes, and they are called antiderivatives. And they are so fun, and we'll start to talk about those in this section as well. Okay, finally, what we need to talk about are different derivative tests that you can use whenever you are curve sketching. And I tried to use some calming colors here for our derivative test because I'm very calm using these. So I'm going to calm down. Okay, pause the video so I can calm down. And we're going to reference these tests as we need to use them in our examples. Okay, so this first test is called the absolute extrema test, or sometimes it's called the candidates test. And it is a test where you specifically are going to use the extreme value theorem because you have a continuous function on a closed interval. Okay, we're not going to look at that in the first example, so I'm not going to say much more about it right now. We will come back and talk about this when we need it. Okay, in the first example, we are going to talk about this one, though, so I want to make sure to discuss this one in detail. This is one of my favorite derivative tests, the first derivative test. Okay, what does the first derivative test do for you? Well, right here, you can see at the very end of step 2 what it does for you. It determines extrema. It determines maxes or mins. Okay, and here's how. You're going to find your critical points, and I'm just going to call the critical point x equals c. Okay, and then what you're going to do is you're going to test the signs of the first derivative around the critical points to determine extrema. Now, I like to show this using what I call an f prime sign chart, or it's a little number line where you mark the critical point. You should also, by the way, mark any restrictions of the function because sometimes restrictions mess this test up. Okay, but then what you do is you look at values along the number line that are on the left of your critical point and are on the right of your critical point, and you plug those into the first derivative to determine the signs of the first derivative. Okay, and actually, if we go all the way back to the warm-up, we can know what's going to happen for our different types of extrema. If the first derivative changes from positive to negative, that means that we have a maximum. Remember that? Changing from positive to negative, the graph is increasing and then it's decreasing, and so that means we have a maximum there. Whoops, did not go as far as I needed to. Okay, so right here I can say that the first derivative is going to be a positive sign on the left and then a negative sign on the right. And if that happens, I have a maximum. Vice versa. Okay, going back, if you want to go back and look at what we wrote for any minimums, and what we said about the first derivative, it was at a critical point, and the sign of the first derivative changed from negative to positive. Think about that. The graph is decreasing and then increasing, and that means that this is a minimum. And finally, if the sign does not change, I lost my spot in my notes just to see if there's anything else. Nope. If the sign does not change around the critical point, so if it stays positive or if it stays negative, that happens sometimes, then this means that we do not have an extreme value at that critical point. So that's one of the first steps to curve sketching, by the way, is to find your critical points and test those critical points to determine maxes and mins. Once you set those points, there's so much other stuff that can just sort of fall into place that you basically have a really good outline of your curve. The other part, though, is understanding the concavity, knowing how the curve curves, right? And where we find that information out is with our concavity test. Grab my other calming color because I'm very calm when I do the concavity test. Okay, here we go. How do you do the concavity test? You find possible points of inflection. And by the way, that's where your second derivative is equal to 0 or does not exist. Hey, maybe we should also note that right here, that a critical point is where your first derivative equals 0 or does not exist. Sorry, we forgot to write that information. That's DNE, does not exist. Okay. Possible points of inflection are where your second derivative equals 0 or does not exist. And then what do? You test the signs of the second derivative around the critical points to determine concavity. That's what the concavity test does. So this is going to look really similar to our first derivative test, but I'm going to call it x equals p, meaning that's our possible point of inflection, instead of x equals c. And I'm going to do our little sign charts again because we're testing the signs of the second derivative. So this is an f double prime sign chart. However, the conclusions that we get out of it will be different because this is not testing for extrema. Notice that it says it is just to determine concavity, meaning how to curve the graph, okay? So there's, again, the three scenarios. It could change from positive to negative. It could change from negative to positive, or you have that no sign change possibility. Okay, but again, what you conclude from this information is very different. Whenever you do a concavity test, that is basically telling you the concavity of the function around the possible point of inflection, and it's only telling you whether this is a point of inflection or not. So actually, no matter if it's changing from positive to negative or negative to positive, what you say about p, about x equals p, is that it is a definite point of inflection. That's it. You don't say max, you don't say min. A point of inflection is almost never, I don't want to say never, never, because I don't know that for sure, but it's almost never max or a min. Okay. I kind of want to say never, never, but I'm not confident. If you have no sign change, that just means that x equals p was not a POI. It actually happens sometimes that your second derivative is equal to 0 or doesn't exist, but that point is not a point of inflection. Okay. Now, I should probably mention before we move on that these little sign charts are actually not valid reasoning steps on an AP exam. So for AP purposes, drawing a sign chart is not enough to say, therefore, I know that there's a max or a min, or therefore I know that there is a point of inflection. As we get further in the year and closer to the AP exam, I'll talk more about what you would need to actually write out. But for right now, for our purposes, these little sign charts will do just fine. And I think you're going to find that they're kind of fun. Okay. Finally, the last test that you see is something called the second derivative test. And at some point I will talk about this, but I don't think we're ready to talk about this yet. I don't know if you noticed this, but the concavity test is a test of the second derivative, but we don't call it the second derivative test. This one uses the first derivative. We call it the first derivative test. That makes sense. This one is using the second derivative, but we don't call it the second derivative test. We call it the concavity test. This is the second derivative test, which is actually a way that you use concavity at critical points to determine whether you have a max or a min. And like I said, you actually could get by just fine without knowing this information right now. So I'm not going to talk about it right now. I think we should just stick to, in example 1, we are going to use the first derivative test and the concavity test. So let's do that. Okay, so I want to finish this video by doing example 1 and seeing how long this video is, and then maybe doing a couple of other little examples with you. Okay, but just so you know, in this video, we will not be doing examples 2, 3, 4, or 5. Okay, doing all of these different functions, it's going to take another video. All right, so let's definitely do example 1, and then I'm going to see where we are at that point. So again, what we're doing here is we're using analytic methods to determine our extrema, our intervals of increasing, decreasing, our points of inflection, concavity, and other relevant information to be able to sketch the curve of the function. Okay, so we don't want to just plug this function into our graphing calculator and do a quick sketch. We want to use the information about the first and second derivative to get a really nice, accurate graph. Okay, usually I teach this as a non-calculator section. This year's a little bit different, but I'm still going to approach it as I'm going to try not to use my calculator, at least for this one. Okay, so one of the first things that I always tell my students to do is note any restrictions of the function. This one, luckily, for our first example, has no restrictions, but I actually like to write that just to keep in mind every single time that that is something we should be considering. Meaning restrictions on the domain. Are there x's that are not allowed to happen here? If so, you have to think about the types of discontinuities you have at those points. And that's really important information to understanding the graph. Luckily for this one, we have just a cubic polynomial function, no restrictions there. Okay, so what do we do next? We find those critical points. They are so important. After restrictions, they are the first thing you should do. How do you find critical points? You take your first derivative and you set it equal to 0 and solve. And you also want to think about if there are any restrictions on the first derivative, because those would be critical points as well. Here, there's no restrictions on the first derivative, so when we set this first derivative equal to 0 and solve, we will have found the critical points, all of the critical points. Okay. Okay, how are we going to solve this? Let's take out a negative 6x common factor, and what we have left is x minus 2, right? Setting each of those factors equal to 0, we get x equals 0 and x equals 2 are our critical points. Next, we test those critical points on a number line. Okay, basically it's like this. We're testing them on this thing over here, okay? But I like to redraw it over here. we test them on a number line like this. And what we are testing them in, or we're testing points around them in, I should say, is the first derivative. I was about to write f prime, but it's y. I'm going to go with y prime because that's how we labeled it here. All right, so at this point, you do not take these critical points and plug them into y prime because you're going to end up with 0. They are the zeros. We already figured that out, okay? But what you do is you think about a point to the left of this critical point. So x equals 0. Think about a point to the left, like -1. And you sub it into the first derivative to find the sign of the first derivative at -1. Okay, I'm going to use the factored form because I'm doing this mentally. So -6 times -1 is positive. -1 minus 2 is negative. Taking a positive times a negative gives me a negative. So I know that my first derivative is negative over here. Now, I didn't actually mark -1 on my number line because -1 was just a number that I picked. Somebody else could pick a different number to the left of 0, fill it in here, and guess what? They would also end up with a negative first derivative. It doesn't matter if you pick -1, -2, -5, -100. It's always going to end up being a negative first derivative to the left of 0. Now let's pick a point in between 0 and 2. Probably every student would pick 1, right? But again, I'm not going to write the 1 because technically you don't have to pick just 1. There's an infinite amount of values you could pick in here. So I'm not going to write 1, but I'm thinking about 1. -6 times 1 is negative. 1 minus 2 is negative. A negative times a negative, though, is a positive. So I have a positive first derivative in between 0 and 2. And finally, let's pick a number to the right of x equals 2, like 3. 3 would be easy. Filling it into the first derivative factored form. -6 times 3 is negative. 3 minus 2 is positive. And a negative times a positive is a negative. Okay, so what does this tell us? It actually tells us a whole lot. It tells us that our function is decreasing to x equals 0. It then changes to increasing between 0 and 2, and then it's decreasing again. So you sort of have an idea of, the shape of your graph, or I shouldn't say the shape, I guess we could say the direction of your graph. Okay. It also tells me that x equals 0 is a min because the first derivative is changing from negative to positive. And remember, the first derivative test tells us, in that case, we have a min. And it tells us that x equals 2 is a max, because the first derivative is changing from positive to negative, and the first derivative test tells us that that's a max. All right, so, if we were doing this without a calculator, I would then say, let's fill these values in by hand, do some calculations here. We can do 0 pretty easily here, just to get a couple ordered pairs to actually plot. So like when x is 0 in the original function, y is -3. Do you agree with that? I wonder if I scaled by 1s as it did here. Yeah, I did. Okay, when x equals 2, what's our y coordinate? That one's a little bit trickier to figure out. Mentally, I do believe in you, and I think you could do it. But you know what? I'm just going to go here and do this just to save us some time and to show you what I'm actually calculating instead of just giving you the answer. I'm taking 2 and I'm putting it into the original function to get the y coordinate when x is 2, and I'm getting a 5. So I'm going to plot the point 2, 5. 1, 2, 3, 4, 5. There it is. Now remember, this is a min and this is a max. So I now know, and I usually use a pencil to do this when I'm teaching it. Do it on like an overhead thing. I now know my function is going down here, going up here, going down here, because my signs of my first derivative tell me that. And I know that x equals 0 is a min and x equals 2 is a max. Okay. Okay, now how do we curve? Well, you could probably just know because it is a cubic function that you are going to curve in this direction and then in this direction, concave up and then concave down. But where's the changing point? Where's the point where we change concavity, or in other words, the POI? Our concavity test will tell us that. So let's take a second derivative, which would be 12x plus 12. Set that equal to 0, okay, and solve to get possible points of inflection. Or if there were restrictions on the second derivative, those would also be possible points of inflection, okay. We don't have any restrictions here, so when we solve this, we get x equals 1. And so that's our only possible point of inflection. Now watch this. I label critical points as CPs, right? Possible points of inflection, they're not points of inflection until you test them on a sign chart or something. You test the signs of the second derivative around the points of inflection, possible points of inflection. So you don't want to just label POI. So I do this. PPOI. PPOI, that's kind of a fun little abbreviation, right? Possible points of inflection. X equals 1 will become a POI when we see that its second derivative changes sign around that value. Okay, so we're going to put 1 on a little number line sign chart. This is a second derivative sign chart, and we're picking a number to the left of x equals 1. We're going to fill it into the second derivative. So what's a number less than 1, 0, right? Filling that in, we get a positive value. So our second derivative is positive to the left. Pick a number to the right of 1, like 2. Fill that into the second derivative. Think about that. Negative 12 times 2 is negative 24 plus 12. Still negative, right? Negative 24 plus 12 is still negative. So we have a negative on the right of x equals 1. Since the sign of the second derivative did change, it doesn't matter if it goes plus to minus or minus to plus. The concavity test tells us that that means that this point that we have on our number line sign chart is a definite point of inflection, meaning it definitely changes concavity there. So we can call x equals 1 a POI. And if it's a POI, it should go up here in our little XY table because we want to plot it. Okay. So again, just to save some time, I'm going to go to my calculator and fill 1 into the original function to find its y coordinate so I know exactly where to plot it. It's at 1. So at the point 1, 1, I have a point of inflection, and that is definitely now where my concavity changes. And this confirms that it changes from concave up, we're going to do like a U for up, to concave down. Then we'll do our frown for down. Okay. So I'm going to erase my lines that I drew, semi-curves, whatever you want to call them. Ooh, I lost 1, 1. Let me plot that point again. And now I'm ready to sketch the curve. Okay, one other thing I kind of want to write out before I sketch this curve is I want to write out some summary information. This sign chart, it's telling us that our function is decreasing from negative infinity to 0 and from 2 to infinity. Again, it's decreasing over those intervals. So I'm going to be starting down and ending going down. Okay, it also tells me that from 0 to 2, that interval, it is increasing. So I'll be going up in this section. The second derivative sign chart, which again is called the concavity test, it's telling me that my function is concave up from negative infinity to 1. It's concave up. And then from 1 to infinity, the function is concave down. Okay, so all of that information put together gives us an idea of how we should sketch this curve. We should be decreasing concave up. This is so hard to do on a Wacom tablet, let me tell you. Okay, decreasing concave up. I'm trying to do this U for up, increasing concave up in here, increasing concave down, down in a frown, decreasing concave down. It's not the best, but let's see how I did. Negative 2x cubed plus 6x squared minus 3. Not bad, right? I could have done a little bit better here, I know. I'm going to blame it on the Wacom tablet. I'm usually better than that. But there we go. There is your very first example of using information from the first and second derivative to graph a function, and that is called curve sketching. Did you love it? And okay, I just checked how long this video has been. It's been an hour. So we're going to end this video with that example. I hope you'll join me for videos 2 and 3, where we will talk about other examples of curve sketching and other examples where we use things like the mean value theorem, extreme value theorem, and antiderivatives. Bye.